Dr. Neelu Dheer from Acharya Narendra Dev College, Delhi University. We have some Viva questions related to our practicals. Define equivalent conductivity, gives its units. What is the effect of dilution on the molar and equivalent conductivity? Why does the equivalent conductivity of acetic acid increases sharply as the solution reaches infinite solution? What is the effect of dilution on the specific conductance? All these Viva questions have been discussed, so I think you will have no problem in answering these questions. Now we come to Kohlrausch law of independent migration of ions. Equivalent conductivity of solution increases with dilution. It was shown by Kohlrausch that the equivalent conductivity of a strong electrolyte lambda approached a limiting value lambda naught of the conductance at zero concentration, which is the same as lambda infinity used to denote equivalent conductivity at infinite dilution. By plotting lambda for a strong electrolyte against under the root C, he obtained almost a linear plot on the basis of which he gave the relation lambda is equal to lambda naught minus B under the root C, where B is a constant which depends on the nature of the salt. The value of lambda naught can thus be obtained by extrapolating the above curve to a value of root C equal to 0. The values of lambda at very dilute solutions of weak electrolytes do not approach their corresponding lambda naught values. The lambda versus under the root C curve does not approach linearity in solutions as dilute as 0.0001 moles per decimeter cube. Thus, the extrapolation method cannot be employed for weak electrolytes. Kohlrausch made a study of lambda naught for different electrolytes and found an interesting relationship amongst the various values. He concluded that each ion contributes a characteristic value of its own to the equivalent conductivity at infinite dilution, irrespective of the nature of the ion present. As we can see from this table, where the lambda naught values of different electrolytes have been noted down, and it was observed that when a bromide ion is replaced by chloride ion, a constant difference of 2.06 is produced in the value of equivalent conductivity at infinite dilution. Similarly, the replacement of potassium ion by sodium ion causes a difference of 23.41 units when the anion remains the same. At infinite dilution, where the dissociation of all electrolytes is complete, including the weak electrolytes, according to Ostwald's dilution law, and where all the interionic effects disappear because of larger distance between the ions, each ion migrates independently of its co-ion and contributes to the total equivalent conductivity of an electrolyte a definite share which depends only on its own nature and not at all on the ion with which it is associated. Thus, the equivalent conductivity of an electrolyte at infinite dilution lambda naught is the sum of the two parts, one due to the cation lambda plus and the other due to the anion lambda minus. Lambda naught is equal to lambda plus naught plus lambda minus naught. In terms of the molar conductivities, the Kohlrausch law for a univalent electrolyte becomes lambda m naught is equal to lambda m naught plus lambda m naught minus. So according to Kohlrausch law, if we have the electrolyte AB, then the lambda m at infinite dilution for the electrolyte AB is equal to the sum of the ionic equivalent conductivities, that is lambda naught A plus lambda naught B minus. And when we have the electrolyte CB, then lambda m naught CB is equal to lambda naught C plus lambda naught B minus. We can subtract the two to get the difference in the equivalent in the molar conductivities of the electrolytes A, B and CB to be equal to lambda naught A plus minus lambda naught C plus. And similarly, for the electrolytes AB and AC, the difference between the conductivities is equal to lambda naught B minus lambda naught C minus. The difference between the lambda naughts of the electrolytes containing a common ion should be equal to the difference in the molar conductivities of ions not in common. For electrolytes other than univalent electrolytes, the molar conductivity can be calculated using the expression lambda m naught is equal to nu plus lambda plus naught plus nu minus lambda minus naught, where nu plus and nu minus are the respective stoichiometric numbers of cations and anions of the electrolyte. Equivalent and molar conductivity of a weak electrolyte is one of the applications of Kohlrausch law. Molar conductivity of acetic acid at infinite dilution can be calculated from equivalent conductivities at infinite dilution of the strong electrolytes hydrochloric acid, sodium chloride and sodium acetate. The acetic acid lambda naught is equal to lambda naught H plus lambda naught acetate ions. To each side of this equation, we add lambda naught of the salt of the strong acid and strong base, that is NaCl. So, lambda naught acetic acid plus lambda naught NaCl is equal to lambda naught H plus lambda naught acetate ion plus lambda naught Na plus lambda naught Cl minus. It can be combined and can be written as lambda naught HCl plus lambda naught sodium acetate, and the lambda naught for acetic acid is made equal to lambda naught HCl plus lambda naught sodium acetate minus lambda naught NaCl. So the right hand side values are known and we can substitute the values to get lambda naught acetic acid. It can be seen in the practice time numerical that we can substitute the values as given in this numerical. The equivalent conductance of sodium acetate, hydrochloric acid and sodium chloride at infinite dilutions are 91, 426.16 and 126.45 at 25 degrees centigrade, and it is required to calculate the equivalent conductance at infinite dilution for acetic acid, and the lambda acid naught acetic acid, which is equal to lambda naught sodium acetate plus lambda naught HCl minus lambda naught NaCl comes out to be 390.71 ohm inverse centimeter square equivalent inverse. Coming to the relation between the equivalent conductivity and molar conductivity, lambda equivalent is equal to kappa by C in gram equivalents per liter. Lambda m is equal to kappa by C in moles per liter. Dividing 1 by 2 we get lambda equivalent by lambda m is equal to C in moles per decimeter cube divided by C in gram equivalents per decimeter cube. For a solution containing W grams per decimeter cube of an electrolyte having molar mass m and gram equivalent mass E, concentration in terms of moles per liter is equal to W by m, whereas concentration in terms of equivalents per liter is equal to W by E. The gram equivalent mass of an electrolyte is equal to m by z, where z is the total positive charge carried by the cations or total negative charge carried by anions furnished by a molecule of the electrolyte on dissociation. So we can write concentration in terms of gram equivalents per liter is equal to W by the equivalent mass, which can be written as W by m by z, which is equal to z into W by m. Thus, concentration in grams per equivalents per liter is equal to z into concentration in moles per liter. So, lambda equivalent by lambda m becomes equal to C in moles per liter divided by Z into C in moles per deciliter. So, CC gets cancelled. So, lambda equivalent by lambda m is equal to 1 by Z, or lambda equivalent is equal to 1 by Z into lambda m. Instead of Z, we can also write nu plus Z plus or nu minus Z minus, where nu plus is the number of cations formed on dissociation of 1 mole of electrolyte and Z plus is the charge carried by one cation. Nu plus Z plus is equal to nu minus Z minus. We can have particular electrolytes like NaCl and CaCl2, where nu plus is 1 and Z plus is 1 for NaCl, and for calcium chloride nu plus is 1 and Z plus is 2. Transference numbers or transport numbers. During the passage of electricity through an electrolyte, there is a contribution to the total conductivity from the positive ions moving to the cathode and from the negative ions moving to the anode. The contribution to the total current by cations may or may not be equal to that made by anions. For example, in a dilute solution of HCl, 82.2% current is carried by H3O plus ions and 17.8% by Cl minus ions. These two contributions depend on the relative speeds of the respective ions and their concentrations. The higher the speeds of the ions, the more current they will carry in any given time. If both the ions move with the same speed, each would transfer the same quantity of electricity. The fraction of current carried by a given ionic species in the solution is called the transport number and is designated by the symbols T plus and T minus. Relation between the fraction of current carried by an ion and its speed. Let us consider two parallel plates d centimeter apart across which a potential E volts is applied, and between these two electrodes some volume of an electrolyte is placed. Let us have in the solution average migration velocity of each cation as V plus centimeter per second. Charge on each cation is Z plus. Total number of cations is N plus. Average migration velocity of each anion is equal to V minus centimeter per second. Charge on each anion is equal to Z minus. Total number of anions is equal to N minus. The condition of electroneutrality requires N plus Z plus is equal to N minus Z minus. The quantity of electricity transported by the cations in 1 second across the plane AB will be equal to the total electric charge possessed by all the cations that lie within the distance V plus from this plane. So, we have the plane AB and the distance V plus and V minus are shown in this figure. Thus, number of cations within a distance V plus from this plane is equal to N plus V plus divided by D. Current carried by these ions I plus is equal to N plus V plus by D into Z plus E. Similarly, the quantity of electric charge transported by the anions in a unit time across the same AB will be equal to the total electric charge possessed by all the anions that lie within a distance V minus from this plane. Number of anions within a distance V minus from this plane is equal to N minus V minus by D. Current carried by these ions I minus is equal to N minus V minus by D into Z minus E. The total current carried by these ions is the sum of I plus and I minus. N plus V plus by D Z plus E plus N minus V minus by D Z minus E. Using the condition of electroneutrality, we get I is equal to N plus Z plus E by D into V plus V minus. The fraction T plus of the total current carried by cations is thus given by T plus is equal to I plus by I is equal to N plus V plus Z plus E divided by N plus Z plus E into V plus V minus. Cancelling the common terms, T plus is equal to V plus divided by V plus V minus. Similarly, T minus is equal to I minus divided by I, which becomes equal to V minus divided by V plus V minus. Now, T plus and T minus are the transport or transference numbers of cations and anions respectively. Dividing these two, we get T plus by T minus is equal to V plus by V minus, or simply the transport number is proportional to the velocity of the ion. The transport numbers of ions are directly proportional to their absolute velocities. When these are equal, that is T plus is equal to T minus, both these ions contribute equally to the transport of the current. However, when V plus is not equal to V minus, T plus will not be equal to T minus, and the two ions will carry different proportion of the current. Experimental determination of transport number. Hittorf's theoretical device. The transport number of ions can be measured by finding the change in the concentration around the electrodes. On passing current through a solution, the factors that result in the concentration changes at the vicinity of the electrodes are the electrode reaction and the migration effects. The electrode reaction. The ions are discharged in equivalent amounts at the two electrodes. The amount of ions in equivalents deposited at the two electrodes is equal to the quantity of electricity in Faraday that is passed through the electrolytic cell. At cathode, cations accept electrons and are deposited on it. At anode, anions are deposited by giving up their electrons. Migration effects. Within the solution, the current is carried by the movement of ions. The amount of current carried by either of the two ions is directly proportional to its ionic speed. Across any plane in the solution, cations move in one direction towards cathode. Anions move in opposite direction towards anode. The sum of the current carried by the ions is equal to the total amount of current that is passed through the cell. When the velocities of the ions are the same, let the electrolytic cell be divided into three compartments: cathodic, central and anodic compartment by two imaginary planes A' and B' as shown in figure. We can see the figure where we have a cathodic compartment, an anodic compartment and the central compartment. The concentration changes are shown when the velocities of the ions are same. We are considering that there are 6 equivalents of electrolytes in each compartment and say 4 farads of electricity is passed through the cell. We can see what happens when 4 farads of electricity is being passed. 4 equivalents of cations are getting removed from the cathodic compartment due to electrode reaction, and 4 equivalents of anions are being removed from the anodic compartment due to electrode reaction. And the since the velocities are same, both the cations and anions carry half of the electricity. So 2 equivalents is being carried by the cations and 2 equivalent is being carried by the anions. Cations are moving from the anodic compartment to the central compartment and from the central compartment to the cathodic compartment. And anions are moving out from the cathodic compartment to the central compartment and from the central compartment to the anodic compartment. Since the velocities are same, 2 farads of electricity is being transported. The changes that occur after passing 4 farads of electricity are changes in the cathodic compartment. We have the electrode reaction. 4 equivalents of cations are deposited at cathode. Migration effects in the cathodic compartment. 2 equivalents of cation move in from the central compartment and 2 equivalents of anions move out to the central compartment. Anodic compartment, electrode reaction is 4 equivalents of ions are deposited at anode. Migration effect, 2 equivalents of cations move out to the central compartment and 2 equivalents of anions move in from the central compartment. Central compartment, there is no electrode reaction. Migration effect, whatever is the migration effect is getting cancelled. 2 equivalent of cations move out, 2 equivalents of cation move in, 2 equivalents of anions move out and 2 equivalents of anions move in. Thus, concentration in the central compartment remains unchanged, while those in the cathodic and anodic compartment suffer changes from 6 equivalents to 4 equivalents. When the velocities of ions are different, let the speed of the cations be 3 times that of anions. Cations will carry 3 times as much current as the anions. Out of the 4 farads, 3 farads will be carried out by cations and the remaining 1 farad will be carried out by the anions. We can again see from the figure, when 4 farads of electricity is passed, according to electrode reactions, 4 equivalent of cations are being deposited at cathode and 4 equivalent of anions are being deposited at anode. And because the speed of cation is 3 times the speed of anion, 3 cations are moving out from the anodic compartment to the central compartment and from central compartment to the cathodic compartment, whereas only 1 equivalent of anion is moving from the cathodic compartment to the central compartment and from the central compartment to the anodic compartment. Consequently, there are no changes in the central compartment. The anodic compartment has suffered a change equal to 3 times that of the cathodic compartment. Thus, for the case of equal speeds, the loss in the concentration of cation due to migration from anodic compartment is equal to the loss in the concentration of anions due to the migration from the cathodic compartment. While for the cases where speed of the cations is 3 times the speed of the anions, the loss in the concentration of cations from anodic compartment is 3 times the loss in the concentration of anions from the cathodic compartment due to migration. This leads to the Hittorf's rule, which I will be discussing in my next lecture. So, I thank you for today and hope to see you soon. Thank you.